Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. As a part of various types of transition metal organometallic complexes, particularly from the perspective of different ligands that exist, we have been talking about transition metal C7H7 complexes, and in that discussion in the last class we have looked into various methods which are available for preparation of these transition metal C7H7 complexes. Now, what had come to the fore in the past discussion that there are about 2 to 3 types of reactions which can eventually lead to the preparation of transition metal C7H7 complexes, and the first of its kind being the substitution reactions in which metal carbonyls are or metal arenes are substituted by treatment with C7H8 ligands. The other method involved reductive coupling, in which metal halides are treated with C7H7 or C7H8 ligands in presence of a reducing agent. We have also seen that photochemically or chemically induced sigma pi rearrangement leading to the formation of these kind of complexes, and lastly we have seen that metal vapor co-condensation methods can also be used for preparation of this transition metal C7H7 complexes. Now today mainly what we are going to be starting off with is particularly look at the reactivity of transition metal C7H7 complexes. Now, of these what comes to the fore is the redox processes of these transition metal C7H7 complexes. Now, what comes to the fore is that replacement of the combination of C6H6 of two, let us say, arene ligands, which can be C6H6 plus C6H6 ligands by C7H7 plus C5H5 shifts the potential for the redox couple in the anodic region. So, the shift is anodic shift. So, the couple is C12. So, overall this can be written as C12 H12 M plus 1 0 couple. So, this means that this can be used for the reaction C12 H12 M plus E giving C12 H12 M 0 reaction, and the E have values which have been measured for certain complexes are to be mentioned over here. We will explain or give some insight on the reactivity of these ligands. So, for example, the E half values versus standard calomel electrode SCE for different complexes of the type C6, H6, M, C6, H6 as opposed to C7, H7, M, C5, H5. So, if one were to look at these E half values for titanium, this is about 0.15 volts, which the positive value meaning that this reduction from +1 to by accepting a electron to become the neutral is favorable. So, that is positive. So, that means this compound is formed favorably as opposed to existing in its cationic form. For example, for vanadium, this complex has a for this complex the 0 plus 1 0 E half value is about minus 0.35, whereas that shifts towards becoming plus 0.26 volts. And for chromium, so this is more towards the anodic shift, more towards the positive region. For chromium, it is minus 0.72 volt, again shifting making anodic shift to minus 0.61 volt. So, what this sort of tells grossly is the fact that these benzene complexes C6H6 complexes are more air or moisture stable, more unstable as opposed to the C7H7M C5H5. So, they are relatively less air sensitive, and that can be easily gauged from this potential values, which says that the formation of these neutral complexes from its cationic state is favored for these C7H7 MC5F5 combination, because these E values are mainly positive with respect to C6H6 metal complexes, where formation of these neutral complexes from its cationic state is less favored, because now they have very high negative E values, which sort of indicates that these are less. And what all of this translates to is the fact that these compounds are relatively or less air sensitive. Now, because of these C7H7M C5H5 complexes being less air sensitive, their like radical cation anions can also be studied or observed. For example, for this complex eta 7 C7 H7 molybdenum M M0 eta 5 C5 H5 radical anion has been observed for M equals titanium and chromium. So, these can further these complexes can further be reduced to the radical anion because their zero neutral state is quite stable. So, then this is an interesting information that we get about the air sensitivity of these C7H7 metal complexes. What we see, the combination of C7H7 metal C5H5, which is equivalent to the combination of two C6H6 complexes of the metal, and what we see that C6H6 complexes of the metal are less or more air sensitive as opposed to C7H7 M C5H5 complexes, which are less air sensitive, and that is primarily because their the E values for formation of the neutral complex from its cationic form has positive E0 values. So, we are going to take a look at the methylation part of the C7H7 complexes, and methylation is an interesting reaction that the C7H7 transition metal complexes exhibit, and the order of readiness is given by chromium becoming less than vanadium, becoming less than titanium. So, order of readiness chromium, vanadium, titanium, and for this mixed CP C7H7 type complexes, like the one shown over here, the metal can be titanium, vanadium, chromium. The lithiation can happen in both of the rings, but requires harsher conditions. For dilithiation, in both C7H7 and C5H5 ring. So, harsher conditions means elevated temperature and or addition of TMEDA. So, these are sort of the conditions in which the methylation can be achieved. So, we are going to take this up with some interesting examples where we are going to follow up these methylation which are possible, and one thing that emerges out that methylation happens at different rings depending on different metal, and that is beautifully illustrated by the example which is given over here. For example, for this compound, the lithiation in the CP ring occurs for vanadium and chromium, whereas the lithiation on the C7H7 rings occurs for titanium and chromium. for titanium and chromium. So, we are going to spend some more time looking at various chemical reactivity that arises from this variation in lithiation and how that leads to generation of or conversion of these lithiated derivatives to many useful other compounds. Similarly, dilithiation of the ring can be achieved in presence of TMEDA, as was discussed earlier, and we are going to see it in this example. Three N Bu lithium TMEDA, and second is R2PCl. Giving this dilithiated product where the phosphonation which arises after lithiation happens in two different rings, whereas if one does the reaction in absence of TMEDA, just taking N butyl lithium and second is R2PCl, then one sees that lithiation happening on the cycloheptatienyl ring. So, the difference lies in this harsher conditions, which is TMEDA, that leads to dilithiation subsequently resulting in phosphonation of both of the rings, and in the absence of TMEDA, if one gives the same reagent, one sees the lithiation happening, but happening at one of the ring, and this ring not being the C7H7 ring, but not of the on the C5H5 cyclopentadienyl ring. Okay. Now, another nice example of this lithiation chemistry on the CP ring is shown over here, and in this case there is iodination reaction which has been achieved for the compounds using C2F4I2 reagent, and we are going to be discussing this over here. So, this is Cp vanadium C7H7 in presence of N butyl lithium, and the second reagent is C2F4I2 in ether, giving this iodination, and in this case the iodination happens at the CP ring. And that with Me3 SN Me3 would give this dinuclear complex, beautiful dinuclear complex, where the Cp is joined by an alkyne linker, and each of the Cp is bound to vanadium. So, thus 2 Cp binding to 2 vanadium and then subsequently each of the vanadium is bound to a C7H7 ring. As is shown over here. So, this is a beautiful work of synthetic chemistry where one can form these dinuclear complexes by sort of achieving lithiation on the selectively on the CP ring. So, actually lithiation is a powerful reaction which is used as a useful tool for synthesizing various kinds of metal complexes, and we see a nice demonstration of this fact in these 4 or 5 different examples which we discussed right now under lithiation, which showed that different types of chemical entities can be synthesized by the selective mono or di lithiation using mild or harsh conditions. So, now we are going to take a look at another interesting reactions, which are addition of nucleophiles. Now, in this is the cationic C7H7 MoCO3 plus complex. Which reacts with methoxide CH3O minus, giving this CH3O. So, CH3O attacking the ring, molybdenum and what is interesting thing over here, that this nucleophile does not go and attack molybdenum, but instead attacks this C7H7 ring, and then as a result this cycloheptatriene is formed, and this attack as discussed over here as well as in other compound is exo attack, which attacks from the outer periphery of the ring. Now, another example of change of hapticity is observed over here. This is also an elegant reactivity in which diversified chemistry is seen. So, this is a nice illustration in which the hapticity of C7H7 ring changes. So, for this substituted molybdenum chloride CO, this is it is 7 compound and 18 valence electron in presence of dimethyl phosphinoethane or DMPE gives this DMP coordinated compound TMP coordinated compound, which also is a eta 3 bound 18 valence electron species, which eliminates carbon monoxide, and this forward reaction is very high yielding, formed in 83% yield, eliminates carbon monoxide to give the eta 7 bound molybdenum phosphate chloride plus 2 CO, and that also is a 18 valence electron compound, and this reaction facilitates CO substitution. So, in this we are going to see another nice example in which a 16 electron compound becomes an 18 electron species by coordination, and this is illustrated in this mixed ligand compound. Zirconium, PME3. So, this is a 16 valence electron species, easily coordinates with the PME3, giving zirconium PME3 adduct of this complex, which also is a 18 valence electron species, and under vacuum this goes back and gives back the 16 electron species. So, with this we come to an end of our discussion on C7H7 complexes for in today's class, and what we had seen is that we have spoken about reactivity of the C7H7 complexes, particularly looking at the various redox processes for present for these C7H7 type complexes, and what we had seen that mixed C7H7 metal C5H5 complexes are slightly less air sensitive as opposed to these C6H6 metal complexes, and also we had seen that these C7H7 complexes translate to many other, can be converted to many other type of compounds via lithiation, and lithiation can be selectively achieved in each of the ring or in both the ring, depending on the conditions in which the lithiations are tried. We have also looked at the nucleophilic attacks, and what we had seen that nucleophilic attacks occur onto the ring instead of the metals, and we have also seen examples where one can see the change of hapticity occurring in these complexes. So, with these I would like to conclude our today's discussion on C7H7 complexes, particularly on the reactivity. A little bit more is left on the reactivity of C7H7 complexes, which would be taken up in the next lecture, and in next lecture we would also be taking up a new ligand, which is C8H8 ligand, and look into their reactivity, synthesis, reactivity and property studies. I thank you for being with me in this lecture and patiently listening to all that has been taught in today's lecture, and I very much look forward to being with you in the next lecture when we finish off with C7H7 ligands and take up C8H8 ligands of transition metal complexes. Thank you and goodbye.